Today's lecture is about RC circuit. As the name suggests, this circuit consists of the series combination of R and C connected across the source of EMF E. In the last lectures, you studied these circuits which consisted of the source of EMF E and the resistor R. There were no other component in the circuit except the resistance R are the resistors R1, R2 and R3. So in such a circuit the current stays constant. But if you introduce this circuit component, that is the capacitor C in the circuit, the current is no longer constant. It becomes a time varying current. Here you can see that there is a switch S connected between the points A and B. You can connect this switch to both the points A or B at a time. If you connect the switch S to the point A, then this source of EMF E comes in connection with this RC series combination. But if you connect this switch to the point B, this source of EMF E gets disconnected. By connecting the switch S to the point A, what happens? This source of EMF E is connected across this series combination, and therefore the current starts flowing in the circuit, and thus this capacitor C will start charging. So for the charging purpose, we connect this switch S to the point A. The current will start flowing in this direction, that is from the positive terminal through R. It will come to the upper plate, and the charging will get started. That is, this plate is connected to the positive terminal of the battery through the resistor R, so this will get positively charged. The upper plate will get positively charged. The lower plate connected to the negative terminal of the battery will get negatively charged. So let's first apply the law of conservation to each and every component. Now this is the seat of EMF, and it supplies the energy to the circuit containing R and C in series. So the work done by this seat of EMF in carrying a charge, a positive charge dq from the negative plate to the positive plate, will be given by E dq. This is the work done by the seat of EMF E in carrying this charge dq from the lower potential to the higher potential. This much is the energy supplied by the seat of EMF to the circuit. Now, according to the law of conservation of energy, this energy must be equal to the energy dissipated across R in form of heat, and then the energy, the potential energy increased in the capacitor C. So this sum, that is the internal energy produced in R plus the increase in potential energy in C equal to du, this sum must be equal to the energy supplied by this source of EMF, which is actually equal to the work done by the seat of EMF in carrying the charge dq from lower potential to the higher potential. So this energy is equal to E dq, the energy supplied. This is the amount of energy dissipated in the resistor R when a current I flows for the time dt in R. This much energy which is dissipated in R is I square R dt. and how much is the rise of potential energy when the charge Q is supplied to the plates of the capacitor having the capacitance C. It is equal to du, and U is equal to Q square divided by 2C. This is the equation which you have already derived in the last chapters. So this value, that is the change in Q square or 2C, will be obtained by differentiating this term. It will be equal to 2Q dQ divided by 2C. So replacing this differential term by its value 2Q dQ divided by 2C, we get this equation. If we divide this equation throughout by dt, then this will become E dQ by dt, and here dt will get cancelled with dt, and here we will be left with Q over C multiplied by dQ divided by dt. So what we have done, we have multiplied this we have divided this equation by dt and obtained this equation. Now dQ by dt is the current I. Here this will also be replaced by I. Now since I is common throughout, so what we can do is to cancel this I throughout, and we will get this equation. The equation which we get after cancelling I is this one. Now this is the equation which we can get by applying the loop rule as well. Look, we have got this equation by applying what? By applying the law of conservation of energy. We have obtained this equation by applying the law of conservation of energy, but the same result can be obtained if we apply the Kirchhoff's voltage rule to this circuit. Now when the switch S connects to A, then the circuit becomes a single loop circuit in which the source of EMF E is connected to the series combination of R and C. So the simple form of this circuit is this. If we traverse this single loop circuit in the clockwise direction and apply Kirchhoff's voltage rule to this circuit starting from this point, the first voltage change is plus E, going from negative terminal to the positive terminal. The voltage change is positive and is equal to plus E. The next voltage change comes about when we traverse this R in the direction of the current. The current is going down the resistor R. So this voltage change is negative and it will be minus IR. The next voltage change comes when we traverse the capacitor C in the downward direction. Now as the upper plate is positive and the lower plate is negative, so we are going from positive potential to the negative potential, or from higher potential to the lower potential. So this voltage change will also be negative and is given by minus Q over C. And then we arrive back at the initial point. We will equate all the voltage changes, the sum of all the voltage changes to 0. So we will get this equation, and then we arrive at this equation, which is exactly the same as this one. So the law of conservation of energy and the Kirchhoff's voltage rule give us the same result for this single loop circuit. Now let's rearrange this equation, and if we rearrange this equation, first we will multiply this whole equation by C. So when we multiply this by C, what happens? E multiplied by C gives us EC. Then there is dq by dt, R multiplied by C, it gives us RC. And then there is Q over C multiplied by C. So C and C will get cancelled and we will be left with Q only. Next, we will move this EC over here to get Q minus EC, and this term is brought to the other side of the equation. It will become negative minus dq by dt RC. Now the next step is to bring this RC to this side and dt to the other side. So dt, this negative minus dt divided by RC. This, when it goes to the other side, it goes to the numerator, and this multiple RC goes to the denominator when we bring it to the other side. So the equation will assume this form, and this Q minus EC will be brought to the denominator on the other side. So we will get dq divided by Q minus EC. So the equation will assume this form after rearranging. Now this equation is fit for integration. Why we have given it this shape? Because we want to determine the value of Q. So for that purpose, we had to separate the variables. The variables in this equation are Q and T. So now let's integrate this equation. Now the integration will be done between the limits 0 to Q for this side and 0 to T for the other side. It means that at T equal to 0, the charge on the capacitor was 0, and at any later time T, the charge was built up to the value Q. So when you integrate the left hand side, this becomes the natural log of this denominator, because in the numerator we have the differential of the denominator dq. So this will become log of this Q minus EC. The limits are from 0 to Q. So the integral of this side is log of Q minus EC with the limits 0 to Q, and the integral of this side is, since minus 1 over RC is constant, so the integral of dt is T, putting the upper limit T, it will be equal to T, and putting the lower limit 0, it will become 0. So all we get is minus T over RC. Now substitute the upper limit in this equation. We will get log of Q minus EC, then minus the lower limit, we will replace Q by 0. So this will become log of minus EC when we put the lower limit. This will be equal to minus T over RC. Now this difference of two logs can be written as this ratio, Q minus EC divided by minus EC. Now how to remove this log? We will raise both sides of the equation to the base E. So here this log gets vanished, and we will be left with Q minus EC divided by EC minus EC. And here when this is raised to the base E, we will get this. So raising this whole equation to the base e, we get this equation. Rearranging, we get q minus ec is equal to this minus ec will get multiplied on the other side with this exponential term, so we get this equation. Q will be equal to, this will go to the other side, CE minus this term. Now taking this CE common, we get 1 over here and minus this exponential term over here. Now this is the value of charge which is appearing on the plates of the capacitor. To obtain the value of current in the circuit, we will of course differentiate it with respect to time. So what we will do is that differentiating this equation with respect to time, the left hand side will become dq by dt, and if we differentiate this side here, 1 is constant, so this exponential term is multiplied with this CE, so minus CE times the exponential term into the derivative of this term, which is and remember we are differentiating with respect to time, so minus 1 over RC is constant and the differential of t is 1 with respect to time, that is we will get dt by dt, which is 1. So this whole is the differential of this side with respect to t. So if we rearrange it, we get here this minus and minus will give you plus, and then we have this c which will get cancelled with the other c in the denominator. So we will get e into this exponential term and divided by r, e divided by r into the exponential term. So this is the value of the current in this circuit. Now an important term in this equation is this product R and C, which is the product of the resistance R of the circuit and the capacitance C connected in the circuit. This product RC is represented by the letter tau, and it is called the capacitive time constant. Now what happens if we put T equal to RC in this circuit? Let's see that at T equal to RC, this T will be replaced by RC, so it will get cancelled and we will get 1 over here. So e raised to the power minus 1 has certain value, and we subtract it from 1, you will get 0.63. So Q will be equal to 0.63 times CE. At which time? At time which is equal to T equal to RC. So T equal to RC gives us Q equal to 0.63 times CE. Now what is this CE? This is the maximum value of the charge on the plates of the capacitor. The capacitance of this capacitor is C, and the voltage source applied across it has an EMF E. So the product of E and C gives you the value of charge which this capacitance C can accommodate, or this capacitor having the capacitance C can accommodate the maximum charge equal to QE or equal to CE. So Q is equal to 0.63 times the maximum charge, or T equal to RC The capacitive time constant is that time in which the charge Q on the capacitor rises to 63% of the maximum value of this of charge on the capacitor. Capacitive time constant T equal to RC is that time in which the charge Q on the capacitor rises to 63% of its maximum value. Now let's see what happens if we put R equal to 0 in this equation. That is, if this resistor were absent in the circuit, then what will happen? Let's see this equation by putting R equal to 0 over here. If R is 0, the denominator of this power becomes 0, so anything divided by 0 is infinity. So E will be raised to minus infinity. That is, we will get 1 over e power infinity. Our 1 over infinity will give us 0. So 1 minus 0 will be equal to 1. And Q will be equal to CE, which is the maximum value of the charge. So instead of this equation, in which Q is equal to 0.63 times CE, we will get Q equal to CE for R equal to 0. It means that this R, or the presence of this R, delays the buildup of charge on this capacitor by a time equal to tau C equal to RC. That is, the charging process, or the increase of charge on this capacitor towards its maximum value is delayed by this much time. If this resistor were not present, the charge would straight away build up to its maximum value CE, but due to the presence of this R in the circuit, it builds up only to 63% of CE in this much time. Tau is equal to RC. Now let's once again refer to this figure in which this source of EMF E is connected to the series combination of R and C. This is providing us a constant voltage or EMF E, and this must be equal to the sum of the voltage across the resistor R, that is VR, and the voltage across the capacitor having capacitance C, which is equal to VC. This sum must be equal to this EMF E, because these are connected in parallel to each other, the series combination and this source. Okay, now let's first consider the situation at t equal to 0. Now the moment this source is connected to this series combination, at t equal to 0, this capacitor is not charged. So Vc, which is equal to Q over C, Vc is equal to Q over C. There is no charge on the capacitor. Q is 0, so Q over C is 0, which means that Vc will be equal to 0 at time t equal to 0. So at time t equal to 0, this term is 0, so E will be equal to VR. That is, the whole voltage provided by this source appears across VR only. So E is equal to VR and VR is equal to IR. In graph, this situation is depicted as this. We have plotted Vc against time and VR against time. So at time t equal to 0, you can see that this Vc is also equal to 0. And at time t equal to 0, this VR is at its maximum value. VR is maximum at t equal to 0 and VC is minimum at t equal to 0. So VC is 0 and VR is maximum, so E is equal to VR at time t equal to 0. So what happens when the time goes on? With the passage of time, you can see that VC is increasing and finally it reaches its maximum value Q over C after some time t, and after the same time t, this voltage across R decreases to 0. Here it is important to note that this E is constant. E is constant because the source of EMF E supplies a constant voltage to this circuit, and that must be equal to E, which will not change with the passage of time. So this is constant in time, and here you can see that this VC is rising with time. So this is not possible that if VC goes on increasing and VR stays constant, it means that this sum will increase and the sum will no longer be equal to E. E will not be constant, in other words, because VC is increasing and VR is staying constant. This is not possible. This would be a violation of the law of energy, law of conservation of energy, because this term is rising, so this side is increasing and this is constant. So this equation will no longer be valid. So in order to satisfy the law of conservation of energy, if this is rising, this must decrease. That is, if one voltage is rising with time, the other must decrease so that the sum remains equal to the constant E. Okay, so at any time t, if you see here, let's say this is the time t equal to 5 seconds, the VC has increased to this much value, but in the same time t, if you see over here, the VR has decreased to this much value. So the increase in VC is balanced by the decrease in VR to keep E constant. So if the voltage across R decreases, it means that since the resistance R of this resistor is constant, so voltage V will decrease only if I decreases. This is constant, so if I decreases, then IR will decrease, or in other words VR will decrease due to the decrease in the current. So when this current decreases, it means that the charge on the capacitor will increase more slowly. So here you can see that initially it is somewhat linear. The increase in the voltage across the capacitor is linear with time to some extent, but then this increase is no longer linear, but it slows down. The curve is bending, so it means that the increase in building up the charge on this capacitor is slowed down due to the decrease in the current. And finally, when it gets fully charged, the current will finally stop or will be reduced to 0. At first the current is maximum and the building up of charge on the plates of the capacitor is linear with time, and then when the current decreases, the build-up of charge on the plates of the capacitor also slows down, which is shown by this bending of the curve, and finally it becomes constant. That is, there is no buildup of charge. When it gets fully charged, no more current will flow to the capacitor. The current will be zero. So when the current reduces to zero, IR reduces to zero, that is, this voltage will reduce to zero as is shown in this graph over here, and at that point the capacitor will be fully charged. So when the capacitor gets fully charged, the current will stop. Now how can you explain it in physical sense? Or its physical significance can be given by the fact that when there is no charge on the capacitor, the current towards the capacitor is maximum. And remember, this current is the conventional current or due to the flow of positive charge. So when there is no charge on this upper plate, the current is maximum, but then the charge starts building up on the plate of the capacitor. This plate is positively charged, so the flow of further positive charge towards this plate will be slightly slowed down, because the positive charge repels the entry of more positive charge. So there is a bend. That is why the current decreases, and the buildup of charge becomes more slow. But due to the potential difference, the current will still flow until and unless this gets fully charged, or the potential across the capacitor becomes equal to E. When this potential difference vanishes, then the current will stop, and at that point, that will be actually the point at which the capacitor has become fully charged. So at that point, VR will be 0 and VC will be maximum. VC is maximum, as you can see here, and VR is minimum. So we can summarize the result that at t equal to 0, VR is maximum and VC is minimum, and at the final time t, VC is maximum and VR is minimum. So at time t equal to 0, E is equal to VR, and at the final time t, E is equal to VC, whereas VR is 0. This is the charging process of the capacitor. Now let's discuss the dimensions of this capacitive time constant, which is denoted by tau and is equal to R and C. We want to prove that this particular term has the dimensions of time. So let's put V divided by I for R, and C is equal to Q over V for the capacitor. So when these similar terms get cancelled, by cancelling both the V's, we get here 1 over I, and I is equal to Q over T, and here we get Q. So Q and Q get cancelled and T comes to the numerator. So it means that this capacitive time constant tau has the dimensions of time, and its unit will be second. So once again, R is replaced by V over I, C is replaced by Q over V. Cancelling the two V's, we get 1 over I here, and I is replaced by Q over T. Here we have Q gets cancelled with Q. We have 1 divided by 1 over T, t goes to the numerator. So in this way, this tau has the dimension of time, and its units will be the unit of time, which is second.